Good afternoon, students. Welcome to the 52nd lecture of fluid mechanics subject. Today we are in Unit 4 discussing about the fluid measurements, fluid flow measurements, measurement of a fluid flow. So in the first class of this, in the first class of this Unit 4, we have discussed about the introduction of the various types of classification of fluid flows and the types of fluid flow channels, right? So in this lecture, we'll discuss about the flow measuring devices. What are the various types of flow measuring devices, right? So, so in the last class, we have discussed about the introduction of the measurement of flow and the various types of fluid types. Today in this class, we'll discuss about what are the various types of fluid measuring devices, the rate of fluid measuring devices, that is a pitot tube, ventimeter, and a orifice meter, right? So we will discuss these topics in this class. So as we said, why we need flow measurement. So mainly for accounting of services like water, gas, steam, etc. Next also plant material balancing and quality control. The necessity is the various necessities we require, such as drinking purpose, agriculture purpose, and industrial purpose, what we already discussed in the last class. So the various types of flow meters that we are using are Ventimeter, which is based upon the pressure difference, orifice meter based upon the pressure difference, rotometer, pitot tube, and magnetic tube, ultrasonic material motor, and turbine flow meter. So in this we are having only to study is Ventimeter, orifice meter, and pitot tube measuring device. Now if you see the concept of the flow measurement, so we are having the accurate measurement of rate of flow, right? So we are having the accurate measurement of rate of flow, rate of flow of fluids or gases. But in this unit, we'll discuss only about the fluids. Okay, accurate measurement of rate of fluids and gases is an essential requirement for maintaining the quality of industrial processes, right? So in every industry, we are having pipes. In every industry, the material what we are using are all types of solids, liquids, and gases, right? So in fact, most of the industrial, in fact, most of the industrial control the flow rates of incoming liquids or gases in order to achieve the control objective. So generally, most of the all industrial companies, they will control the incoming liquids and gases, which is a basic primary objective. As a result of which, what happens, the accurate measurement of flow rate is very important to achieve. So whenever you are maintaining the flow rate of the liquids and gases, automatically the flow rate also can be measured with this concept. Next one, it could be volumetric or mass flow rate. So in order to find the flow rate, in order to find the flow rate, in order to find the flow rate, so it could be the volumetric type or it may be the mass flow rate. The medium could be gas or liquid. As we are discussing about the flow rates of a fluid or a gas, it could be measured in the volumetric or it could be in the form of mass, right? The measurement could be intrusive or non-intrusive. As a result, there are different types of flowing measurement techniques, right? So there are various types of flowing measurement techniques that are used in the industries, The common types of flow meters to find the industrial applications are, right? The common types of flow meters that find industrial applications are as follows. See, what are they? The first one is the obstruction type of flow meters. First one is a obstruction type of flow meters. That is differential pressure or variable area. Differential pressure means pressure in the pressure difference and or variable area. So the various types of obstruction type of flow meters are orifice meter, pitot tube, and venturi meter. Right. Second one, inferential type of turbine. Inferential type of turbine. Third one, electromagnetic type of device. Electromagnetic measuring device. Fourth one, positive displacement. Positive displacement type of motor. Positive displacement type of motor. Next one is fluid dynamics. Fluid dynamic device. Sixth one, anemometer. Anemometer. Next one is ultrasound meter. Next one is a mass flow meter. So like this, we are having various types of flow meters which are used for measuring the flow rate. But according to your syllabus, we are having only three types of meters, that is orifice meter, pitot tube meter, and a venturi meter. Right? Next, for the dynamics of the fluid flow, what we have already studied in the second unit, the dynamics of the fluid flow or hydrodynamics, the fluid motion is studied. The fluid motion is studied, including the force and energy considerations, right? Including the force and energy considerations. Next one, types of energy. What are the types of energy here? We are having three types of energy whenever we are considering the fluids or gases. Fluids or gases. So what are the three types of energies here? Potential energy, pressure energy, and kinetic energy. Okay, so we will discuss these things already we have discussed earlier, but in a brief. Why? Because we are studying in the flow meters, we are studying in the flow rate meters. We will discuss just in brief. First one is potential energy. It is the energy possessed by the fluid particle. It is the energy possessed by the fluid particle due to its position with respect to an arbitrary datum. With respect to the arbitrary datum, that is nothing but a potential energy. Next one, pressure energy. It is the energy possessed by the fluid particle due to its pressure. So whenever a fluid is in the container, so whenever it is possessing some pressure, it is nothing but a pressure energy, right? Third one, kinetic energy. It is the energy possessed by the fluid particle due to its motion or velocity. Due to its motion or velocity, right? That is nothing but kinetic energy. Okay, it is the energy possessed by the fluid particle due to its motion or velocity is known as kinetic energy. Next one. So why we are discussing this type of things means, so in this unit 4, we are discussing about the flow meters. We are discussing about the flow meters. In that, we are having three types of meters, that is orifice meter and pitot tube and venturi meter. So these three things are the applications of Bernoullis equation, right? Bernoullis equation. So that's why we require to study the three types of energies, that is potential energy, pressure energy, and kinetic energy. Next one is Euler's equation. So before discussing about the flow meter devices, that is a venturi meter, orifice meter, and pitot tube, we should definitely know the basics of Euler equation, Bernoullis equation, and the types of energy. So that's why we are discussing the fundamentals of this one, and later we switch on to the types of measuring devices. Okay, so coming to the Euler equation, what are the assumptions and limitations? So the Euler equation says that the fluid is ideal. means it is a non-viscous or non-friction losses. There are no friction losses or non-viscous fluid. Next one, the fluid is incompressible, right? The fluid is incompressible, that is the fluid is constant. That is the second assumption. Third one, the fluid is steady. The fluid is steady flow. Fourth one, the velocity of a flow is uniform over the section. So whenever the fluid is flowing in any section, there the velocity of the fluid is uniform. Next one, only the gravity and the pressure forces are considered. Next one is only the gravity and the pressure forces are considered. Okay, no? Next one is only the gravity and the pressure forces are considered whenever you are doing this type of Euler equation assumptions. Next, coming to the equation, for the steady flow of an ideal fluid, consider an element AB, consider element AB as shown in the figure. So if this is the figure, so based upon this, right? So dz plus dp by gamma plus v dv by z is equal to 0. Coming to the Bernoullis equation, integrating this Euler's equation, so z plus p by gamma plus v square by 2g is equals to constant. We get Bernoullis equation, right? So where z is equals to potential energy per unit weight of a fluid or potential head with respective to an arbitrary datum. Okay, na? Next one is p by gamma is a pressure energy. P by gamma is pressure energy per unit weight of a fluid or a pressure head. Next one, V square by 2g. It is a kinetic energy per unit weight of a fluid or velocity head, right? So we got the potential energy, the pressure energy, and the kinetic energy, right? In some cases, you are instead of Z, you can see H in some other textbooks also. Okay. Now applying the Bernoullis equation between the 2 points, section 1 and so if it is a section 1 if there is a pipe flow, ఇది మనకి సెక్షన్ 1 అనుకున్నప్పుడు, ఇది మనకి సెక్షన్ 2 అనుకున్నప్పుడు, this is section 1 this is section 2. Okay, now applying the Bernoullis equation, we get the between the 2 points of the fluid flow, we get z1 plus p by gamma 1 plus p square by 2g into 1 at section 1 is equals to z2 plus p by gamma 2 plus v square by 2g 2, that is equal to constant, right? That is equal to constant. Now applying the Bernoullis equation for a real fluid flow, actually a real fluid flow does not exist in the nature, but coming to the Bernoullis equation applying for the real fluid flow, the real fluid flow has a viscosity that resists the flow, so that a part of the total energy of a fluid is lost due to the friction. This head loss is denoted by HL. Head loss is denoted by the HL, right? Therefore, pressure energy, this is a potential energy, pressure energy plus kinetic energy is equals to pressure and potential energy, pressure energy plus kinetic energy plus datum line plus datum head loss plus head loss, right? So this is the formula for the real fluid flow, right? Bernoullis equation for a real fluid flow. The direction of the flow, the fluid flows from a point at a high total energy to that of the low total energy, right? As we know that the direction of the flow is generally from the high to low, right? So the fluid flows from the high total energy to the low total energy. So this is about the Bernoullis equation, right? By using this Euler's equation. Understood? Now, based upon this formula, we will do the problems. In Ventimeter, orifice meter, and pitot tube. And pitot tube, right? Next applications of the Bernoullis equation. Where you are using Bernoullis equation, there are many practical applications of Bernoullis equation. We shall consider only 3 applications for the fluid measurement in the pipes. So Bernoullis equation is applied to various types of applications, but as we are discussing about the measurement of flows, as we are discussing about the measurement of flows, only we are using 3 types of applications for this flow measurements. What are the 3 types of applications here? That the 3 types of applications are of hydraulic applications, hydraulic devices, that is Ventimeter, orifice meter, and a pitot tube. So these are the 3 types of devices where we are using in the application of the Bernoullis equation, right? Now we'll discuss these 3 in detail. So that's why in order to get the introduction of this orifice meter, Ventimeter, so directly I didn't jump into the topic. So I gave the importance. Actually, Bernoullis equation. So we have discussed the Bernoullis equation in the unit 2, right? So unit 2 lo manam Bernoullis equation gurinchi maatladukunnam. So there we stopped, and again we are starting in the unit 4. That's why the applications of Bernoullis equation. So we are starting this with this 3 devices. So now we'll see these devices, each and every one, by using some problems. We'll see the first one is Ventimeter. First one is a Ventimeter. It is a device for measuring the discharge of a liquid. So it is a hydraulic device for measuring of the discharge of a liquid, discharge of a liquid flowing in a pipe. So how the fluid is discharging in a pipe. So as shown in the figure, it consists of 3 parts. So the Ventimeter consists of 3 parts. One is convergent cone or inlet, throat, and divergent cone or outlet. Simply, the Ventimeter consists of 3 devices or parts. What is first one? Inlet. Second one is throat. Third one is outlet. See the figure here. So this one inlet, this 2 is outlet. The middle, the neck portion is the throat portion. Or you can write this figure, or you can draw this figure also. Okay. So this one is, so the section 1 is a inlet, the section 2 is outlet, the section 2, the center point where it is having the location is throat at a distance of x, right? This is the simple concept of a Ventimeter, right? The inlet is a short pipe that converges from the pipe diameter 1, right? What is the meaning of inlet here? The inlet is the short pipe. So see the figure. So ikkada the inlet should be short distance, the outlet should be big distance, right? So based on that, the inlet is a short pipe that converges from the pipe diameter d1. So diameter d1 is small diameter d2. So initial diameter is d1, so final diameter is d2. So it is converging like this. So diameter 1 నుంచి కిందకి తగ్గుతుంది, right? This convergent pipe converts the pressure head into the velocity head. During this action, what happens? During this conversion of the convergent pipe, it converts the pressure head into the velocity head. Next, the second one is the throat. The second part enti the throat. First part is the inlet, second part is the throat, third part is the outlet. Okay. Now the throat is a small circular pipe with constant diameter d2. So see the figure. So this is d1 అనుకున్నప్పుడు, this is d1 means this is d1, this is d2. Okay, this is d2, where you are having the diameter of this first one and the diameter of this throat. is due to maintaining a constant circular pipe diameter, right? Next, the outlet is a longer pipe that diverges from the throat of diameter D2 inch to the pipe diameter D1. Only what happens the third component in this third component? So whatever the throat diameter D2 is there, from there it is making a divergence. Means it is slowly keep on increasing to some level, that is a D2, and remaining constant at the D2 to D1 diameter. So whatever the diameter is there in the first conversion, that is in the inlet, the same diameter is there for this outlet. Okay, see the figure. So from here again it is taking the same D2 diameter and coming back to the diameter of the D1. That is the meaning, right? This divergent pipe converts the velocity head into the pressure head. So what happens here? It converts this pipe converts the velocity head into the pressure head. So the inlet pipe flow, it converts pressure head to velocity head, but here velocity head to the pressure head. So that is the difference between the first part and the second part of the Ventimeter. Okay, next. So this is the figure for this Ventimeter. Now, if you see for ideal real fluid, by applying the Bernoullis equation between the sections 1, 1 and 2, section 1, 1 and 2, 2, representing the inlet and the throat respectively, as shown in the figure. See here, though this is a inlet, this is a outlet, this is a throat. Okay, we are maintaining the datum line XX. Now with this, we'll derive the formula for the Ventimeter. Now see, D1 is the diameter of the inlet. Section 1 దగ్గర D1 is the diameter of this inlet, right? Second one, P1 is a pressure at section 1, right? At section 1, P1 is a pressure. Next, at V1 is the velocity of the velocity at the section 1, that is inlet, velocity at the inlet section 1. Next, A1 is the area at the section 1. So what we are taking in the section 1? We are taking pressure, velocity, acceleration. Therefore, at the same time, D2, P2, V2, A2 are the corresponding values of the section 2 of the section 2, that is at the throat point. Okay. Now taking these values into consideration, applying the Bernoullis equation at the section 1 and the section 2. So what we are doing here, applying the Bernoullis equation at the section 1 and section 2. And what you are getting, just see here, applying the Bernoullis equation, this is a P1 by rho g plus W1 square by 2g, or we can keep W1 square by 2g plus datum energy. Z1 is equals to P2 by rho g plus W2 square by 2g plus Z2. So what you are getting, as the pipe shown in the figure is horizontal pipe, that is horizontal pipe and the datum energy is equal to Z1 is equal to Z2. Whenever the pipe, this is the base anukundam. From this base, if this is a height, so if this is a pipe flow, if this is a pipe flow like this, if this is a pipe flow, what's happened here? So here the Z1 and Z2 value will differ, but here what it is saying that, but here the pipe is horizontal pipe, the datum energies are equal, that is Z1 is equals to Z2. Now P1 by minus P2 by rho g is equals to V2 square minus V1 square by 2g. So as this one and this one will get cancelled, so this one will get cancelled. So P1 minus P2 by rho g is equals to V2 square minus V1 square by 2g, right? Therefore, what is the H here? H is equals to V2 square minus V1 square by 2g. Okay, so where H is equals to P1 minus P2 by rho g. That is the difference of the pressure heads at the section 1 and 2. For the continuity equation at section 1 and 1 we get a continuity equation A1 V1 is equals to A2 V2, and VA V1, take V1 or V2 is equals to V1 is equals to A2 V2 by A1. Now what happening? Now what is the H here? H is equals to V square by 2G. H is equals to V square by 2G. V square by 2G. Okay. Now V square by 2G into A1 square minus A2 square by A1 square. Okay. Therefore, V2 take this side. V2 is equals to A1 by root of A1 square minus A2 square into 2GH into 2GH. Just this we have simplified. Then later, what is the discharge? Discharge Q is equals to A into V, area into velocity. Therefore, discharge Q is equals to A1 V1 is equals to A2 V2, or A1 V1 is equals to A2 into H value. What is the Q here? Q is equals to A1 A2 A1 A2 by, so this A1, this value. Okay, so A1 A2 by root of A1 square minus A2 square into 2GH. That is a discharge derivation. Okay, discharge derivation. Now, this is the equation of the venturimeter for measuring the discharge of ideal fluid that is flowing in the pipe. So, whenever you are coming across any questions in the venturimeter, what is the formula you are saying? The formula is this one. Okay, so Q is equals to A1 minus A2 root of A1 square minus A2 square into root 2GH. This is the equation of the venturimeter that is flowing in a pipe flow, right? Now, an actual discharge that will be less than the theoretical discharge. So that is the actual discharge what we got. But whenever you are calculating the discharge, it is theoretically less than the actual discharge. Then what is the Q actual discharge here? Q actual discharge is equals to C into D, C D C E into A1 minus A2 divided by root of A1 square minus A2 square into root 2GH. Therefore, CD is a coefficient of venturimeter. CD is coefficient of venturimeter, and always the value is less than 1. So this is the basic formula for this discharge. Okay. Next, expression of H given by differential U2 manometer. So this is extra material, extra information that is also is there in this chapter. But expression of H given by the differential U2 manometer. So in the case 1, the liquid is in the manometer. The liquid in the manometer is heavier than the liquid in the flowing through the pipe. Right or wrong? The liquid in the manometer is heavier than the pipe flowing through the pipe. Therefore, for that H is equals to X of SH minus S0 minus 1. So I think this will not come in the exam, just for your information we are discussing. Then coming to the first problem of this venturimeter. What is the first problem? So a venturimeter is 15 centimeters inlet. Ante first part, the inlet diameter, and 10 centimeters throat ఇచ్చాడు. అంటే ఇనిషియల్ గా 15 ఉంది, తగ్గేసరికి 10 వచ్చింది. Laid horizontally in a pipe. Okay, in a pipe to measure the flow of 0.9 specific gravity. Then reading of the mercury manometer is 2 meters, 20 centimeters. Then what is to find? Calculate the discharge in the liters per minute. Okay. Now write the given data, and what is the inlet is given? The inlet is what is the area? A1 is equals to pi 1 d1 pi d1 square by 4. And what is the pi value? You know that. What is the d1 value? D1 value 15 centimeters. 15. So ఇక్కడ centimeters లో తీసుకున్నారు. So all take all the things the centimeters only. 15 square by 4, that is equal to 176.7. Then same thing for outlet. What is the diameter? A2 is equals to pi d2 square by 4, that is equal to pi into 10. What is the throat? The throat is 10 centimeters. That is a 10 square by 4. That is a so and so value we have got. So and so value we have got. Next, H is equals to hm into gamma m by y minus 1. That is equals to final formula for this, the reading of the mercury, which are using the 20 centimeters. Okay. Now, what is the formula Q? What you have derived in the first case? Q is equals to A1 into A2 root 2 GH divided by root of A1 square minus A2 square. So, applying all the values, A1 value, what is A1? 176. A2 value 78 into root 2 G into H 28.282.2. What is the H here? The H is the total value is 282. So write this application. A1 value, A2 value, root of 2 into 9.81 into 28.2. Now substituting directly by using this formula, we can solve the problem very easily. Only the very fast and so applying the values here. So finally we have got this solution. So what's the time? Next, second problem. Now see, a 30 centimeter into 15 centimeter ventimeter is provided to the vertical shape line. Here the ventimeter is vertical pipe line carrying the oil. What is the oil? 0.9 specific gravity. 0.9 specific gravity. The flow direction is upwards. The difference in the elevation between the inlet and the throat is 30 centimeters. What is the difference here? It is a 30 centimeters. Now the reading of the mercury manometer is 25 centimeters. 25 centimeters, right? Now see, what is the thing to calculate? Calculate the discharge. Calculate the pressure head between the inlet and the throat. So for the inlet, what we require? Diameter is the inlet. Diameter is the input. A1 is equals to pi d1 square by 4. That is equal to pi into d1 in the, it is given as 30 centimeters. Pi 1 is given as a 30 centimeters. Therefore, pi into 30 square by 4, that is equal to 706.8 centimeter square. Then what is the outlet? What is the throat here? Throat area ఉంటుంది కాబట్టి A2 is equals to pi d square by 4. That is pi into what is the throat? 15 centimeters square by 4. That is 176. Then what is the H you have to find? So see here the H formula. Okay. So coming to the throat value, we got the area. Therefore, H is equals to hm gamma m by m gamma minus 1. Therefore, 25 hm value is 25. Hm value is so the reading of mercury manometer is hm value is 25. So what is this 25? 25 half, 13.6 gamma m, 13.6 gamma m, which is given, divided by 0.9 minus 1. The value is 352.8 centimeters of oil. Got it? Next. Now, after doing this one, what is a Q? Discharge value, discharge formula. Q is equals to A1 into A2 into root 2GH, right? A1 into A2 into root 2GH divided by root of A1 square minus A2 square. That all we have done. Therefore, substituting directly the values, A1 value 706.86 into A2 value 176 root of 2 into G into H value. Under this root of A1 706.8 and 176.6. So after getting solved by this problem, so finally after doing all the simplification, finally we got the solution. Q is equals to so and so centimeter cube. Right? Next, what is the second thing to find? So first one discharge kanukunnamo. Second thing is determine the pressure head between the inlet and the throat. So second one formula, what is second formula? Z1 plus P1 by rho down to the power minus Z2 plus P1 by Y, P1 by gamma, that is equal to H. Next, what is the second one? So P1 by gamma minus P2 by gamma plus Z1 minus Z2 is equals to 352.8. Now Z1 minus Z2 is equal to 0. That is Z1 minus Z2 is Z1 is equal to 0. Z2 is equals to this minus 30. That is equal to minus 30. Now P1 by gamma minus P2 by gamma is equals to 352.8 plus 30. That is equal to 382 centimeters of oil. Now, so till now we have discussed about the horizontal type. So next one is inclined type. Next one is a vertical venturimeter, right? I think hope you're understanding the concepts, right? So for a horizontal venturimeter, reading of the manometer HM is employed to get H. Capital H, in order to get it, we have to read the manometer reading. As discussed before, H is equals to H. Employed to get H. H is equals to potential head plus pressure head. That is the meaning of the H, right? It is the reading of manometer HM is employed to get the H value. But the H value now is potential hand or potential head plus pressure head, right? So potential head plus pressure head. Next one, for inclined type of venturimeter, see here for a horizontal type. So this is the datum line. Then find the height తీసుకొని you have to draw the figure. So drawing rough figures, eligible figures, and neatly visible figures in the thing is very easy to find. Now see here, potential energy plus pressure kinetic potential energy plus pressure head energy. Next, for the inclined venturimeter, when the venturimeter is inclined, the potential head changes. Okay, that's why for some applications these are not used. So with this, we'll stop the class as the time is running out. So we'll discuss the class in the next session. So we'll have sessions, normal sessions on the inclined type of